Alright, let's talk about exponential equations first. And one of the first things we're going to look at is when you have 16 is equal to 2 to the x power. Now, we don't have a method for solving for a variable when it's in an exponent, but we can use what's called the one-to-one property. And that says that if you have the same bases, okay, so it's going to be critically important that you have the same base. So base to the x equals base to the y. So if that is true, then it must be true also that x is equal to y. And that makes sense. I shouldn't have to convince you of that. But it's an important, powerful thing for us to remember and for us to use. So, it's easy. Let me give you an easy example. If I said 3 to the x plus 1 is equal to 3 to the 4th power, could you solve for x? And of course the answer is, oh yeah, that's pretty easy. Then x plus 1 must equal 4, so x is equal to 3. And you have an answer. Okay, so that's great, no problems. Now let's go back to the original equation, and we look at this and say, well, that's great, but I can't use the one-to-one property because I don't have the same basis. I have a 16 to the 1, if you want an exponent, is 2, and the base is 2, so that just doesn't work. So you have to be able to write them in the same basis if it's possible. And in this case it is possible because I can write 16 can be written as 2 to the 4th power. So now 2 to the 4th power is equal to 2 to the x. Ah, there we have it. Same basis, therefore x must equal 4. Alright, so why don't we try another one like that? What if I said, let's try 5 to the x minus 3 is equal to 1 over 5. Okay, well, let me think about this. It's kind of like the same basis, but not quite, since it's a 1 over. What I can do, this is already in a base 5. I can write the right-hand side in a base 5 if I use a negative 1 exponent. So, therefore, x minus 3 is equal to a negative 1, and adding 3 to both sides gives me x equals 2. So I'm able to solve that. So it's going to require that you're very good with your rules of exponents. So let's do one more. I reminded you about a negative exponent. Let's do one more to remind you of fractional exponents. Why don't you try this one? Let's say 4 is equal to, oh, I got to give it something here. 4 to the x is equal to, let's see here. I was trying to do a fractional exponent, wasn't I? Oh, let's do it this way. 16 cubed. Okay? So right now you look at that and you say, oh, those aren't the same bases. But actually, I remember 16 can be written as, I'm not going to get the 1/2 in here, am I? Sorry. 4 squared. So that's my 16. 16 still needs to be raised to a 3rd power, and that's going to equal 4 to the x. But this will be a good reminder of what to do with your powers of exponents. You got a power raised to a power. So of course you're going to multiply those exponents. 4 to the 6th. Aha, x is equal to 6. Alright, so that works really great solving an exponential when you can get to same basis. Alright, let's talk about those equations where you have bases on different sides of the equation that you cannot write the same way. They can't both get to a base 2 or any common base. We're going to go back again, though, to the one-to-one property, but this time for logarithms. And that says if some number is equal to a number, then it must be true that the log of m is equal to the log of n. Okay? So if the two numbers are equal to each other, then their logarithms must equal. So what we say about this is we're basically taking the log of both sides. So you'll hear me say that all the time. What should I do with this problem? And I'll tell you, take the log of both sides. And this is what I'm referring to. Alright, so let's try one problem like that. What if I had 15 is being raised to the 3x, and that's equal to, I don't know, some number 7. Okay? So, gosh, I'm not going to get those in the same base, so I'm going to go ahead and take the log of both sides. Log 15 raised to the 3x is equal to log of 7. Okay, so I haven't really helped myself yet until you remember the most important thing from last lesson was that power rule, which allowed us, when you have a logarithm, to take the exponent and bring it down in the front. So here we are, that's really important. 3x times the log of 15 is equal to the log of 7. See what I've done? Now I don't have a problem with x in the exponent. I'll divide the left-hand side by everything that's not x, so 3 to log 15, and I have to do that to the right-hand side. Okay, I'm back, and so of course the 3's cancel, log 15's cancel over here, and I get x is equal to log of 7 divided by 3 times the log of 15, and of course I'm going to throw that in my calculator and get a nice approximation, remember, because I won't be able to write down all the digits. So that is great. Okay, that was a phone call from York County canceling school tomorrow. I'm really hoping we get in tomorrow. Okay, so we're going to try one more of these kind of problems where you're going to take a log of both sides. And that would be something like, 3 to the x plus 1 is equal to something oddball like 10. Okay, so you're going to look at that and say, wow, I need to solve for an x that's an exponent. That means I should take the log of both sides. So take log of both sides as our strategy. And when we do that, the log of 3 raised to the x plus 1 is equal to the log of 10 because of our one-to-one property. That allows us to bring this exponent down in the front, and I'm going to be really careful in this case because of that plus sign. It's binomial to use parentheses. Log of 3 is equal to log of 10. So x plus 1 is equal to log 10 divided by log of 3, and then I can subtract 1 from every side. And so x is equal to this expression here, where I divide the logarithms, get that answer, then subtract 1. Okay. Alright, let's talk about solving logarithmic equations, and we've really already looked at the one case where you have a log on one side is equal to a log on the other, and so you have to have a log of something. So log of x is equal to the log of 2x minus 3 or something. And what happens is you really can just, it's that one-to-one property that says if the two logs are equal to each other, then without the logs, the numbers are already equal to each other. So x is equal to 2x minus 3, and simply x is equal to 3. Alright? So that one's pretty simple when you have just log on one side, log on the other. And this can happen if you have a log minus another log equal to 0. Okay, because of course you can take the log to the other side. So if you want to try that one, that would be real simple. I'd have to take the log to the other side first. Is equal to log 2x minus 1. Okay, and once I've taken it to the other side, now I can just go ahead and write it out and solve again for x. Okay, but let's look at the other case when you do not have just a log, and it gets a little messier. Let's say you just one log, so it's a log base of something of x is equal to 5. Now, I'm certainly not going to take the log of both sides like what our last strategy was. So the strategy here is going to be write it as an exponential. Okay, so that's using the if and only if statement. If and only if 3 to the 5th is equal to x. And I can just throw that into the calculator. I'm good to go. Alright? So that's pretty straightforward. So being able to write them back and forth, that if and only if statement, is vitally important to have that really well. It gets a little more interesting when you have, you know, two logs and something else. So let's say we have two logs. So let's say we had log some base of x plus log of the same base, always has to be the same base, of 3 is equal to 4, or something like that. Alright, so what we're going to do is, we cannot use the if and only if statement, the definition, to write it as an exponential because there's two logs instead of just one. So we need to condense those using the properties we learned before. So remember, when this is an add, these two things are going to multiply. So I end up with a single logarithm. I multiply those two together, and I have a single log. Now I'm ready to use the write it as an exponential strategy. So the base to the exponent is equal to 3x, and x is equal to the fourth is 16, and divide by 3. And that's how you solve a log equation. Okay, why don't you guys try one? Let's see, you try this one, and I'll kind of highlight some of the algebra that might come up. Let's say we had a log, any base, of x plus 1 minus a log, same base, of x is equal to some number 7. Okay, try it. Remember, you're going to condense the logarithms first and then write it as an exponential. Okay, you might have gotten this far, and it's actually a little bit trickier than I expected this one to be. Not exactly what I was planning, but I'm going to walk you through the last of this one. You're trying to solve for x, but the problem is I have too many x's. So, first thing I'm going to say is I have a fraction, I want to get rid of it. So let's multiply both sides by x. So 6 to the 7th, some crazy big number, times x, is equal to x plus 1. Okay? Now, everything with an x goes to the left, everything that's not an x stays to the right. So 6 to the 7th x minus x is equal to 1. Now, that's just, you know, a number. If this was, you know, just a 6x minus x, you'd call it 5. But now we have this big number. Let me see if I can find it really quick. Problem is I don't have a light on. 6 to the 7th. 6 raised to the 7th. 279,936 minus 1 is 2,709,935x is equal to 1. So x is equal to 1 divided by this big old number. And that would be a great answer. Alright, we'll see you in class.